Okay, sorry about the break there. A little technical difficulty. So let me go back to this slide out of the formal use of identity elimination. So on the left-hand side of the screen, I've got an argument consisting of statements in FOL. Cube A is identical with B, therefore cube B. Okay. The conclusion here is the logical consequences of the premises by way of the principle of the indiscernibility of identicals. Right. The formal rule that we're going to work with in our system of natural deduction that expresses the indiscernibility of identicals is again, identity elimination. Okay. So when I construct a formal proof, right, using the conventions of Fitch, I start out by listing my premises, one line after another. Right? Then below, right, all of those premises, the conclusion. And strictly speaking, if you're using the conventions of Fitch, there should be a vertical line, right, to the left of all of the statements making up the argument, and a small horizontal line with the premises above it, and any statements generated from those premises according to rules below that line. Okay. Here, the only statement that would be below that line would be cube B. Okay. Another part of the conventions of Fitch is that when you generate a statement, a new one, based upon what you've already got, including the premises, and you do this according to a rule, you cite the rule off to the right of the new statement. And if that rule is a rule that generates this statement from previous lines in the proof, you state the numbers of those previous lines as well. Okay, so in this case, the only line that I've generated, the only statement that I've generated is cube B. Okay? I did that from the identity elimination rule, and so I wrote that off to the right. And in order to apply this rule so as to generate cube B, I relied upon line 1 and line 2. So I write 1 and 2 off to the side of the rule. Okay, so I've got identity elimination followed by 1, 2. Okay, just to be clear about this, that tells the reader, right? 3, that's been generated according to rule on the basis of lines 1 and 2. So on the right of the screen, I show how this looks in our bit of software that's called Fitch, right, named after this famous logician. The only difference here is that the premises are in a different order, right? And that actually raises a fairly important point. You can use the identity elimination rule regardless of the order of appearance of the given statements with which that rule works. Okay, that rule is always going to work with like at least one identity statement, like A is identical with B, and some other statement. It doesn't matter if the identity statement occurs first in the list or second in the list. Okay. So let me now just make a little bit of a note something about the identity of indiscernibles. The identity of indiscernibles is a different principle than the very similar sounding. The indiscernibility of identicals is a different principle than the very similar sounding identity of indiscernibles. Indeed, they sound so similar that I sometimes get the two confused. The latter principle, that is the identity of indiscernibles, states that no two objects are exactly alike. And so if A and B are exactly alike, well then, like, A just is B. I mean, we're talking about the same thing, right? If what's called A and what's called B are exactly alike, there's just one thing, not two. The former principle, the one on which identity elimination, of which identity elimination is the formal expression, has an important non-trivial implication. That is that the language we are working with does not involve what is called an intentional context. So yeah, I mean, again, identity elimination, that's a formal expression of the indiscernibility of identicals, not to be confused with the identity of indiscernibles. So it's a formal expression of the identity, of the indiscernibility of identicals. That principle has a non-trivial implication, right? Something follows from that principle, non-trivially. It's important. And what follows is this: the language that we're working with when we work with that principle does not involve what's called an intentional context. Okay. So if you're working with this principle on which identity elimination is based, okay, that implies that the language that you're working with does not involve an intentional context. So an intentional context refers to a stretch of language, either a whole statement or part of a statement, in which we cannot assume that names refer to actually existing objects, or in which we cannot assume that when A is identical with B, everything true of A is also true of B. English, as a matter of fact, very often involves these so-called intentional contexts. And that's intentional with a lowercase s, by the way. That is not a misspelling. It's a technical term. So English very often involves intentional contexts, as when we talk about Pegasus. Okay. We can talk about Pegasus. Strangely, we can even say seemingly true things about Pegasus, right? Like Pegasus is a mythological creature, or Pegasus had wings, right? But the name Pegasus does not refer to an actually existing object. So that's one intentional context where we talk about, I guess you call them like fictional objects. Here's another one, when we talk about what someone believes. Okay. So for example, suppose someone believes that the morning star is Venus. Okay. Suppose it's also the case that the morning star is identical to the evening star. Okay. Suppose these are different names for the same object. Okay. By the identity of indiscernibles, it seems like it should follow that the same person believes that the evening star is Venus. Right? They believe the morning star is Venus. The morning star and the evening star are the same object. Right? By the identity of by the indiscernibility of identicals, right? If A and B are the same, what's true of one is true of the other. This person believes, right, that the morning star is Venus. It's true of the morning star that this person believes it's Venus. The morning star is the evening star, so it seems like it should be true that this person believes that the evening star is Venus. Right? Like that should follow by the indiscernibility of identicals. But of course it doesn't. Because the person in question might not know that the morning star and the evening star are identical. And so they might very well believe that the morning star, oh yeah, that's Venus, but not believe that the evening star is Venus. Okay, right. So that's another kind of intentional context. one case is where people talk about objects that don't exist, right, by name. Another case is where we're talking about what someone believes or intends or hopes or what have you. Okay, these are contexts where the indiscernibility of identicals does not hold. Okay. If a language or stretch of language does not include intensional context, it is said to be extensional. Since the indiscernibility of identicals is assumed to hold for FOL, and all names in FOL refer to actually existing objects, FOL is what's said to be an extensional language. And that in turn implies that it has considerably less expressive power than English. Okay? So you can say some things in FOL that you can also say in English. But there are many more things that can be said in English that can be said in FOL. There's lots and lots of English. Actually, when you begin to examine it, lots and lots of it, right, involves these intentional contexts. FOL is free of those. It's a thoroughly extensional language. Okay. So we are introduced to a few other rules, actually just two other rules in chapter 2. As I warned you, usually when a rule is introduced, it's going to be paired with another rule. Okay, so there'll be a symbol, and it's either going to be like symbol elim or symbol intro. You can then expect that there's going to be another rule involving the same symbol. Okay, so we're going to get pairs of rules for the most part. Intro rules and elim rules, right, having to do for each pair with some symbol. So we've been introduced to identity elimination, right? Stands to reason that there's going to be an identity intro rule. The intro rule basically tells us this: for any name in our language, an expression asserting that an object so named is the same as that object so named may be introduced at any point in the proof. So that's a perhaps unhelpfully complicated way of saying that. Look, I mean, if A, right, is a name that you're working with in FOL, so right, you assume that A refers to a unique, actually existing object. If that's a name that you've got at your disposal, A, you can enter into a proof at any point. A is identical with A. So I have an example here. My premise is A is identical with A. It does follow from that I have as a premise A is identical with B. It does follow from that A is identical with A by identity introduction. This follows because A is identical with A is the kind of statement that follows from anything. It's another way of putting it. It's a logical consequence of anything. Indeed, it's a logical consequence of nothing at all. Right? One can introduce such a statement at any point in a proof, regardless of what you've got to work with, regardless of what the premises are. Indeed, you can enter that into a proof without there being any premises. Last part of this argument. Therefore, ultimate conclusion here, B is identical with A. And that follows by the identity elimination rule, 2 and 1. Right. Our other rule is the reiteration rule. And that rule tells us that if some woof, call it P, has appeared anywhere on a line by itself in a proof, it may be generated as the next line, that is reiterated. Right? So my example is relatively actually a very simple one. Suppose you've got as your one and only premise to work with A is identical with B. Well, then by the reiteration rule, you can just say again, on the next line of the proof, A is identical with B. Okay. Of course, right, that almost always, in fact, probably always would not be a helpful thing to do, right? To basically just repeat the immediately preceding line of proof. However, there are occasions where the reiteration rule is helpful. And on those occasions, typically you're going to be like reiterating, saying again, a statement that occurred considerably earlier in the proof. Why would you want to do that? It's going to turn out to be the case that there are some proofs where that allows you to do things more quickly than if you did not have the reiteration rule. Okay. All right. Okay, now just a note on relations. This note is important for the homework assignment from last time. Using identity elimination and identity intro, our authors are able to provide proofs illustrating a number of features of the identity relation. Okay. So first off, identity is reflexive, so that everything is identical with itself. For example, A is identical with A. The identity relation is symmetrical, so that if A is identical with B, right, it follows that B is identical with A. It's also transitive. They actually provide a proof of this, at least by way of an example, so that if A is identical with B and B is identical with C, then A is identical with C. Okay. So, yeah, reflexivity, symmetry, transitivity, these are features of some relations. All of them hold true of the identity relation. Okay. Some of them hold true for other relations, like taller than. Taller than is transitive, right? Like if A is taller than B and B is taller than C, then A is taller than C. Okay. Sibling, that would be a symmetrical relationship, right? Because if A is a sibling of B, then B is a sibling of A. Okay. Okay. Some relations, furthermore, are inverses of one another. So that if F, and then in parentheses AB, then G, in parentheses, BA, and vice versa, where F and G basically stand for two different predicates. Okay. In the language of Tarski's world, left of and right of are such relations, since left of AB implies right of BA, and vice versa. Note that this was a key for successfully completing homework exercise 1.9. So in that exercise, you were asked to translate into FOL, right? Given certain names to work with and certain predicates, some sample English sentences, and one of the predicates that you were supposed to work with was owned, right? One of the sentences, though, that you needed to translate into FOL was couched in the term belongs, or the phrase belongs to. Okay, owned and belongs to, they are loosely speaking, somewhat loosely speaking, those are inverse relations. Okay? If A belongs to B, then B owns A, right? If belongs to AB, then owns BA. The relationship between those two concepts is rather like the relationship between left of and right of, or taller than and shorter than, larger than and smaller than, and so forth. Okay, a couple more notes. There's one more rule that's introduced at this point. And it's really a rule that's in here for pedagogical purposes. The authors supply it basically as a means to try and help you understand this concept of logical consequence, or a valid argument. Okay? It's a rule that you're going to need to use to do some of the homework at this point. As though we make more progress in introducing this, the rules of this system of natural deduction, you're not going to be called upon to use this rule very often or even at all. Okay, so it's sort of a stopgap measure at this point. Okay. In any case, as the slide says, some of the homework exercises present you with problems for which the official rules that have been introduced so far are insufficient. In most cases, that is because a logical consequence, in the case in question, depends upon the meaning or meanings that predicates have in the language of Tarski's world, that is the blocks language. So here's an example of logical consequence in the blocks language, in the language of Tarski's world. Suppose you're told that A is between B and C. It's a logical consequence of that claim that A is between C and B, right? Okay, if one is true, two must be true. It's impossible for one to be true and two false. So we've got a case of logical consequence here. Why? How so? What rule could we invoke, right, to generate two from one? What rule that we've got could we invoke to justify that move? As I explained in the slide, the conclusion here is a logical consequence of the premise. But this is not a matter of the, I should say, the indiscernibility of identicals, let alone identity introduction or reiteration. Logical consequence in this case is a matter of the meaning of between, specifically the conditions on which wolves formed by between are true in Tarski's world. Obviously, some statements having to do with right of are logical consequences of statements having to do with left of, for similar reasons. In these cases, you should use the Anacon rule to justify such steps in a formal proof. Okay. One more note about the Fitch software. So when you add a new line, okay, it's going to prompt you off to the right for the rule, and you're going to be able to click on the prompt, and it'll bring a drop-down menu, and you can select what rule you want. It does not allow you to just type in the numbers of the lines that the rule is working with. Okay? Instead, what you do is you highlight, right, by clicking on the line or lines that you think the rule applies to in order to generate the new line. Okay. There is a tool, I think it's under proof, right, at the top of the Fitch screen, that allows you to display, having highlighted certain lines, the numbers of those lines next to the rule that you invoked. But that's not the way it originally shows up. Okay. Originally, you just select from the menu of rules the rules you want to invoke to justify this new line, and you highlight the preceding lines in the proof that you're applying that rule to so as to generate the new line. Okay, so last thing, I don't have a slide for this, but it needs to be discussed because it has to do with the last part of the reading assignment for this week, and also the last bunch of homework exercises. So proof is a method for establishing that an argument is valid, right? If you've got a proof that it starts with some premises and ultimately leads to, as the last line, the conclusion, you followed the rules for generating new statements throughout, um, that establishes that this argument is a valid argument. The conclusion is a logical consequence of the premises. What if, though, you can't find a proof? Well, just because you can't find a proof doesn't mean there isn't one. So what I'm getting at here is that proof is a method for establishing validity. It's not a method for establishing invalidity. It's not a method, in other words, for establishing non-consequence, right? For establishing that the conclusion is not a logical consequence of the premises. So, how can we do that? How can we establish non-consequence, if not by proof? And the answer is to construct counterexamples. Okay. So again, the notion of logical consequence is very closely related to the concept of validity. A valid argument is one where it's impossible for the premises to all be true and the conclusion false. Here then is how you can establish invalidity and by extension, non-consequence. Come up with a counterexample, right? Come up with a case. It can be imaginary. It's fine, but just some case, a possibility, right? Such that all the premises are true relative to that case, relative to that possibility. But the conclusion on those perhaps imaginary conditions, possible conditions, the conclusion is false. Okay. In the exercises, right, towards the end, some of those arguments are in fact invalid. They're arguments in the block language about objects in Tarski's world. They're invalid. Okay. You can't prove this in our sense of proof, because proof establishes validity. It establishes logical consequence, not non-consequence. Well, what do you do then? Well, here's what you do. Go into Tarski's world and create a counterexample. Create a world where all of the premises in that argument are true, and in that same argument, in that same world, the conclusion is false. If this can happen even once, the argument is an invalid argument. Okay. And I myself, when I do these exercises, if I want to make totally sure that I'm dealing with the counterexample, here's what I'll do. Of course, you can not only in Tarski's world, like, populate a world on the left-hand side of the screen on that chessboard. You can also create woofs, sentences, statements, right, in the block language on the right of the screen. So what I would do is if I want to be really careful about this, I would write the argument in question on the right side. Okay, just type in the sentences, the statements, the woofs, one by one. And then I would try to construct a world where every one of the premises is true and the conclusion is false. And then, just to make absolutely sure that I'm dealing with a counterexample, have the program check the truth or falsehood of all of the statements in that argument. Okay? If I do that and I see every one of my premises gets a T and my conclusion gets an F, I know that's a counterexample. Okay, so that's a good way to go about, I think, proving invalidity, establishing non-consequence, right? For arguments having to do with Tarski's world, arguments in the block language. Okay. So it's a good way of going about doing the homework for that section. Counterexamples generally are the way to go when trying to establish non-consequence for arguments having to do with things other than like Tarski's world. Okay, say someone has given you a deductive argument. They mean for that argument to be valid. So they mean for it to be the case that there's just no way all the premises can be true and the conclusion false. You don't think so. you think this is invalid. How do you show that? Just come up with a possible case, right? Come up with a possible scenario where all the premises are true and the conclusion false. And that will establish non-consequence. And that is all I have for now. One note before I go, though, last note. What I'm going to do week by week is, once all the homework has been collected, go over it and try to figure out what people are having a hard time understanding, if anything. Okay? If I can isolate a few things, right, I will then go ahead and produce another video going over the homework, especially the exercises that people seem to have the most trouble with. I don't know if that's going to happen this week, because so far the homework seems to have gone really well. I don't anticipate, though, all of us being trouble-free from this point forward. So expect usually for there to be 2 videos. The first longer video, typically, covering that week's new material, and a second shorter video later in the week, probably about Tuesday, going over the homework, troubling parts of it from the previous week. And that is it for tonight.